Hello and welcome to another video. In this video we're going to be working on number of connected components in an undirected graph. And this is going to be the next video in TypeScript line 75. So you're given a graph of n nodes and an integer n and an array edges, where AB means there's an edge between A and B. Return the number of connected components. So a connected component means like everything in that component is connected essentially. So this will be one, and this is another, and in the second example, everything is connected, so there's only one. So this is a perfect problem for the UnionFind algorithm, and I think this is actually on the UnionFind Explore card. So I'll briefly talk about the UnionFind, and I'll show the code for it. It's something I would recommend just memorizing, but essentially what a UnionFind does is it takes some input n, and it has three functions. So it has a find, which gives you the parent of a node, a union, which connects two nodes, and you can have an isConnected, which will tell you if nodes are connected. But to be honest, we don't really need this isConnected. What we can do for the union is we can connect two nodes and return true if we connected them, or false if not. And basically the way this UnionFind works under the hood is it has like an array of parents for every single node, and it has ranks, so it's optimized. But yeah, something you definitely want to look into if you haven't like looked into the function. But essentially, let's kind of walk through this problem and how it would work with a UnionFind once we do have that data structure. So let's go through this example one. Essentially, what we're going to do is we're going to have n equals whatever we have, n equals 5. And then for every edge, we're just going to try to connect the two nodes. And if it's possible, so let's think about it, right? Let's say we have some nodes. Like I said, we have some nodes. For every possible connection, so right now we have n, like when there's no connections at all, we have n connected components, right? Every node is a connected component by itself. It's not connected to anything. So every time it's possible to make a new connected component, that means we reduce it by 1. So if we can connect two nodes, so let's say we can connect these two, now we have one less component, right? We have 1, and then 2, 3, 4. And if we can make another connection, now we have 3, and so on. But a connection that would be invalid in UnionFind is something like this, because this is already connected, right? So these three are already connected. So UnionFind just makes sure to only connect things that aren't connected already. So it's very useful. So essentially, let's kind of walk through this example and the edges. So here, we're going to start out with 5 components. And we're going to say, okay, for 0, 1, can we connect them? Yes, they're not connected at all. So we're going to connect 0 and 1. Now for 1 and 2, can we connect them? Yes, they're not connected. 2 isn't part of this, so we're going to connect 1 and 2. So this is all part of one component now. And then for 3 and 4, can we connect them? Yes, they aren't connected at all, so we can connect those as well. And then, so we were able to make 3 successful connections. We started out with 5 nodes, so 5 minus 3 equals 2. And similarly up here, let's try to walk through this one. So for 0 and 1, are they connected? No, so we can connect them. Are 1 and 2 connected? No, 2 is by itself, we can connect it. Are 2 and 3 connected? No, we can connect those. 3 and 4 we can connect as well. And so we made 4 successful connections. We started out with 5, so now we have 1 connected component. And essentially what happens is if you aren't able to make a connection, like let's say here, let's say we tried to connect 2 and 0. Let's say there was an edge 2, 0. We would try to connect it, and we'd say, okay, well, we can't. So we essentially just skip that one. That connection isn't made, and n remains the same. That's pretty much it. You just loop through all your edges, check if you can connect them, and then for every connection you make, you have 1 less component, because when you connect 2 components, you make 1 component, right? So that's 1 less component. And that's basically it. So as long as you know the UnionFind data structure, you're good for this one. So let's look at the code. And I'm going to briefly go over the UnionFind. So essentially you have a roots array and a ranks array. And the roots keeps track of the parent of each node, and the ranks keeps track of the longest path to get to the node. And you just initialize every node to be its own parent, and the rank of every node to be 1. Find recursively gets the parent of every node and optimizes the path. And union basically just checks, let me get the parent of 2 nodes. If it's the same, then they are already connected, so let's return false. Otherwise, let's connect the 2 nodes, and let's make sure to connect them optimally. So you just want to connect them so that the shortest path to the root stays the same, or stays as low as possible. And I will link the UnionFind data structure to where it talks about it in depth, but essentially explaining the entire UnionFind from like nothing to optimized. It's probably like 30, 40 minutes. So I would recommend you learn that first, and then when you learn that, this is a super easy problem. You can also, by the way, so if you wanted to, you could do like a DFS here with a visited set. That would also work, right? for every, you would just say like, okay, let me just make like an adjacency list, and then let me start at every node. So let's say you make these edges, then essentially you would start at every node. So what would happen is like you would start at node 0, and then you would traverse to every single node possible, put those all in a visited set. So you'd have like 0, 1, 2 in a visited set. Then you would try to go to node 1, and you'd see like, okay, well, node 1's in my visited set, so I can skip it. Node 2's in my visited set, so I can skip it. And every node you can make a DFS from is a connected component. So you'll make one when you start at 0. Then when you get to 3, you'll try to make another. And then you'll also encounter 3 and 4 with a DFS. So then your visited set will be full. And then you'll basically have 2 DFSs. So then you can just +1 here. And this is like, I think I did like a hard problem that was kind of like this, where essentially instead of doing UnionFind, you just DFS everywhere possible from every node, and if your node was visited, you don't do a DFS, and essentially every node you start at, it's kind of like, kind of similar to like number of islands, those types of things, very similar situation, right? Anytime you start at a valid location, you just go through everything you can get to and mark it all visited, and then you skip starting at any location that's visited because you've already encountered it. So that also works if you don't want to use a UnionFind. But with a UnionFind, really easy. So you just have a UnionFind, make a UnionFind. UnionFind takes a number n for n nodes, so we just pass in n. Then we can just do a for each or a bunch of for loops. So we can just say edges for each. Let's take an element, and then let's just say start node n node equals that element. And we just try to union them, right? So if UnionFind.union start end, then we will decrease our number of connected components. Otherwise, we can just move on. And finally, once we're done looping through all the edges, we can just return end here. Yeah, that should be it. So let's try that. And you can use a normal for loop, whatever you want. Literally just go through your edges, try to connect them all. Every successful connection, reduce the components. And that did work, I think. Oh, it didn't. Undefined, interesting. So let's look through our, I think I copied the UnionFind correctly, so this is probably somewhere here, I'm guessing. Oh, right, we just returned. Okay, so we got to return n at the end instead of nothing. And there we go. So you could see it's a pretty efficient solution. And let's talk about the time and space for this one. So for UnionFind, to make a UnionFind, you have an array roots and array ranks, and those are equal to the size of n. So that's already length n, where let's just call this the vertices, maybe. We'll use vertices and edges. So that's already vertices. And then for every edge, you have to make a union. And so a union is O of 1, roughly. It's a little bit slower, but it's roughly O of 1. So a union's O of 1, a find is also O of 1, roughly. So this is going to be E, right? For every edge, you try to make a union, which is O of 1. So this is however many edges you have here. And yeah, I believe that's all for the time. Now let's look at the space. So for the space, this UnionFind data structure, right, is the length of the number of vertices we have. So that's O of n. And for edges, we don't really even create the edge. We just union it in place, right? We don't create an adjacency list of edges or anything. For UnionFind, it's just O of v. Like the only really data structure we have is roots and ranks, which are both just O of the number of vertices you have, number of nodes. And yeah, that's pretty much it for this problem. So not too bad as long as you know UnionFind, literally the perfect use case for UnionFind. So I definitely encourage you to do that. You could do it with DFS, but if you are practicing UnionFind, perfect problem for it. So, and this is basically as easy as it gets for UnionFind. So hopefully you like this one, and if you did like it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.